Welcome to this video on linear regression, where we'll break down one of the most fundamental concepts in data science and machine learning. Whether you're a student, a professional, or just curious about how data can predict future outcomes, this video is for you. We'll start by understanding the basics and then apply them to a real-world example, so stay tuned. So, what exactly is linear regression? In simple terms, it's a method to understand the relationship between two variables. Imagine you want to predict house prices based on their size. Linear regression helps you find that relationship, allowing you to estimate the price for any given size. It's like drawing a line through data points to observe the general trend. Linear regression isn't just a theoretical concept. It's widely used across various industries. From predicting stock prices in finance to assessing risks in healthcare, and even optimizing marketing strategies, this technique is a go-to for analysts and data scientists. Understanding linear regression is a crucial step in harnessing the power of data to make informed decisions. To give you a better idea, let's look at some real-world applications. In finance, linear regression is used to predict stock market trends. In healthcare, it helps assess patient risks based on historical data. And in marketing, it's used to analyze customer behavior and predict future buying patterns. These are just a few examples of how linear regression is making a difference in the world today. Now that we have a basic understanding of what linear regression is and why it's important, let's dive deeper into how it works. We'll start by exploring the theory behind it and then move on to a hands-on example. Let's get started. In linear regression, our goal is to find the best-fitting linear equation that describes the relationship between input variables, also known as predictors or features, and the output variable, also known as the response variable. Essentially, we want to draw a line through our data points that best represents this relationship. The equation of a line in linear regression is written as y equals mx plus b. Here, m represents the slope of the line, which indicates how steep the line is. The b is the intercept, which tells us where the line crosses the y-axis. And x is our independent variable that we use to predict y. The line of best fit is crucial in linear regression. It's the line that best represents the data points in our plot. We find this line by minimizing the distance between each data point and the line. This method is called the least squares method, which aims to reduce the total squared distance of all data points from the line, thereby providing the best possible fit. There are a few key assumptions in linear regression that help ensure our model works well. 1. Linearity. We assume a linear relationship between our independent and dependent variables. 2. Independence. Each observation should be independent of others. 3. Homostasticity. The variance of residuals should be consistent across all levels of the independent variable. 4. Normality. The residuals should follow a normal distribution. Understanding these assumptions helps us ensure that our model is valid and our predictions are reliable. To derive the line of best fit, we start with our linear equation, y equals mx plus b, where m is the slope and b is the intercept. Our goal is to determine the values of m and b that make this line best fit the data points. To achieve this, we use the least squares method. The least squares method minimizes the total of the squared differences between the actual data points and the predicted values on the line. Mathematically, we are trying to minimize the sum of the squared residuals, where each residual is the vertical distance between a data point and the line. To calculate the slope m and intercept b of our best fit line, we use these formulas. This tells us where our line crosses the y-axis. By calculating these values, we ensure that our line fits the data points as closely as possible. The mean squared error, MSE, is our cost function in linear regression. It measures how well our line fits the data by calculating the average of the squared differences between the actual values, yi, and the predicted values, hat yi. The formula is text MSE equals frac 1n, sum y hat yi care 2, where n is the number of data points. The goal is to minimize the MSE, which means reducing the total squared error between our line and the actual data points. By doing so, we ensure that the line we've fitted represents the data as accurately as possible. Let's move on to a practical example to see how these concepts come to life. We'll walk through a data set, apply linear regression, and interpret the results. Now that we've covered the theory, let's move on to the practical part, implementing linear regression using scikit-Learn in Python. This powerful library makes it easy to apply machine learning algorithms with just a few lines of code. Before we implement linear regression, let's take a moment to understand what scikit-Learn is and why it's so popular. Scikit-Learn, also known as Sklearn, is a powerful and easy-to-use Python library for machine learning. It offers simple and efficient tools for data analysis and modeling, making it a go-to choice for both beginners and experts. The first step in our implementation is importing the necessary libraries. We'll use pandas for data manipulation, NumPy for numerical operations, linear regression from Sklearn for creating our model, train test split to split our data, mean squared error to evaluate the model, and matplotlib for visualization. Before we can build our linear regression model, we need data to work with. In this example, we're using the diabetes dataset, which is a commonly used dataset for regression tasks. The dataset contains several features related to health and lifestyle, and our goal is to predict a target variable, which is a measure related to diabetes progression. We'll start by loading this dataset from a CSV file using pandas, a powerful library for data manipulation in Python. Then, we'll take a look at the first few rows of the data to understand its structure and contents. Now that we've loaded and explored our dataset, the next step is to define our independent and dependent variables. The independent variables, also known as features or predictors, are the inputs we use to make predictions. In this example, we'll use several features from the dataset as our independent variables. The dependent variable, also referred to as the target or response variable, is what we aim to predict. Here, it's a measure related to diabetes progression. After defining these variables, we'll split our data into training and testing sets, which is a crucial step in building and validating our machine learning model. Now that our data is ready, the next step is to create and train our linear regression model. We'll initialize the linear regression model and fit it to our training data. This will allow the model to learn the relationship between our features and the target variable. With our model trained, it's time to make predictions. Here's how we do it. We use the predict method of our trained model to generate predictions based on the test data. This is done with the line ypred equals model.predict xtest. The predict method takes our test features, xtest, and returns the model's predicted values for the target variable. We then display the first few predictions with print, ypred of 5. This helps us quickly check the initial output of the model and gives us a glimpse of how the model is performing on the test data. Now it's time to evaluate our model. We calculate the mean squared error, MSE, to measure how well the predictions match the actual values. We'll also create a scatter plot to visualize the relationship between the actual and predicted values, which helps us understand how well our model fits the data. In an ideal scenario, we would expect the points in our scatter plot to be closely aligned along the diagonal line where predicted values equal actual values. This would indicate that our model is accurately predicting the target variable. However, in our case, the points are more dispersed. This is expected because our model is relatively simple and we've only used one feature for prediction. A more complex model or additional features might better capture the relationship between the variables and improve the alignment of the points. So, while the spread is normal for this simple setup, it also highlights the potential for enhancing the model by incorporating more features or using more advanced techniques. So now, let's train the model using all the features from our dataset. I'll walk you through the entire code and explain each step. First, we start by importing the necessary libraries. We use pandas for handling data, NumPy for numerical operations, linear regression from scikit-Learn for our model, train test split to split the data, mean squared error to evaluate the model, and matplotlib along with Seaborn for visualization. Next, we load the data from a CSV file into a data frame using pd.readcsv. This function allows us to easily read the dataset and get a look at the first few rows with print_df.head. After loading the data, we prepare it by separating the features and the target variable. We drop the target column to get all features into X and define our target variable Y. We then split the data into training and testing sets using train-test-split. This function helps us divide the dataset so that we can train our model on one part and evaluate its performance on another. Now, we initialize our linear regression model with linear regression and fit it using the training data. This step trains the model to learn the relationships between the features and the target variable. With the model trained, we proceed to make predictions on the test data using model.predict. We then calculate the mean squared error, MSE, with mean squared error to assess how well our model is performing. Finally, we compare the actual values with the predicted values using a scatter plot. The plot shows how closely our predictions match the actual values. As you can see, there's some difference compared to the previous model that used only one feature. However, while the performance has improved, it's still not perfect. To further enhance the model's accuracy, we might need to consider additional steps like data preprocessing or using more complex models, which we'll cover in future lessons. For those eager to dive deeper, I've linked a helpful article in the video description, Linear Regression Made Simple. You can also find the code from today's video on my GitHub. Check the description for the link. In the next video, we'll start a series where we apply linear regression to real-world projects. This hands-on experience will solidify your understanding before we move on to the next set of algorithms. If you have any questions or ideas, drop them in the comments below. I'd love to hear from you. And don't forget to like, share, and subscribe to stay updated with the latest content. Thanks for watching, and I look forward to seeing you in the next video.